If I go live, and we are good to go. So are you good to go?
I'm good to go.
All right, let's get into it. So welcome back to the channel, you Scholars of Enlightenment. Today we have another tech roundup with CEO of Focal Point Positioning, Ramsey Faragher. He's our tech guru. As you can see on the screen, he's been called the real life Q by Top Gear magazine. He's also one of Wired's 32 innovators who are building a better future. So today we're going to be going through the biggest tech news from the last month. We're going to be talking about GPS on the moon, Chinese fusion reactors, another Mars rover, and hopefully much, much more. But before we start, Ramsey, a couple of the topics that we discussed last month have had, what shall we say, a little bit of garnish added to them. So last month we were talking about Tesla, not Tesla, yes, Teslas, weren't we? We're talking about Teslas. Yep. And there'd been a horrible crash in Texas last month. And the response of Elon Musk at the time was to say, oh, well, various sensors can be dropped from Teslas. We don't need various sensors. We don't need the radars. They're a bit of a liability. What has been the development with that? And can you just remind us what the use of those radars and lidars and sensors are on the autonomous Teslas?
Yeah, so there was a couple of interesting things that happened since we spoke last. So we talked about how it's very challenging to fuse the data together from the radar and the cameras, and that they were clearly struggling with it. But the right thing to do is to solve that problem and keep them both and use them both properly.
Yeah.
And it looks like they've announced that they're going to drop the radars completely. So it might help stop the Teslas from hitting inanimate objects, which is the problem they're having. They keep hitting things like overturned trucks that are stationary on the freeway and things like that. And the issue is to do with the fact that radars have to delete everything that's static relative to the Earth and only pay attention to things that are also moving relative to the Earth.
So radars are good for the sort of ranging measurements of the car, where it is in relation to other things that are moving around in the environment. And the LiDAR things are more for absolutely positioning things in the world. Is that a fair summary?
The problem with radars is that they give you a very fuzzy blob of the thing you're paying attention to, but they can tell you very, very accurately if you have any closing speed relative to that. So cars look like a big fuzzy blob, but a radar is very good at telling you that you are currently a fixed distance from that big fuzzy blob and that you're not getting any closer or further away. But it's this mess in front of you. And the challenge they're having is that all of the static objects in the world still look like a big fuzz, and therefore the car can't tell whether something is sticking into the lane or not, because of the big fuzz. So they have this challenge of trying to ignore all of the big fuzzes that are static relative to the Earth, like trees and lampposts and stuff, and only pay attention to radar returns from objects that are also moving, like the other cars on the freeway. So in order, I guess, to try and solve this problem where there's confusion between the radar information and the visual information, the camera information, when they see an overturned lorry and stuff like this, is to get rid of the radars and just rely on the cameras, which is bold move, because the reason that you normally don't just rely on cameras for autonomy is because of issues of rain and fog and dust and poor lighting and darkness. And you normally want to augment your system with as many possible sensors as possible, including the brilliance of radar, which can tell you a lot more than cameras can about relative closing speeds and stuff like this. So it's a risky move, and they're gambling that they'll be able to get all of the information they need from just the cameras. And what we saw a few days ago is that there's been a Tesla photographed with lidars on it, which is another technology that Tesla don't use at the moment, which is laser radars. They don't have the fuzz problem, but they're more expensive. And it's likely that all Tesla are trying to do is use the lidar information on some test cars to help train the AI part of the system that uses cameras. So they're probably still going to stick with just camera only systems, but they're going to have tried to train the map using lidars and possibly other sensors that they don't deploy. So it's an ever evolving story really on that front, and the jury, I suppose, is out. You would normally add more sensors if you're having fatal crashes that you can't resolve.
I was going to say, there seems to be a little bit of a tension between the removal of these sensors. You've got Elon Musk saying, you know, we're going to remove the radar. LiDAR is a crutch, it says here in this article. There seems to be a bit of tension between what he's saying and what would seem to be the optimally, you know, tech-based or scientific-based solution for this, which would be just have more information. Or is there another competing metric with cost or weight or whatever it might be?
Exactly. The holy grail is that your autonomous vehicle only has a few £100 worth of clever sensors on it. So the original lidars that, when I was working on autonomous vehicles that we mounted to cars, were about £75,000 for a spinning laser on the top of the roof of the car. And that is obviously just never ever going to scale. You know, they want to have autonomous vehicles that cost a grand total of about £10,000. So putting a £75,000 lidar on the roof is never going to fly. So there's companies that have become now billion-dollar companies because they're pioneering really cheap lidars. I think Luminar being one of them. But this is the big challenge that you've got, that ideally we'd put lots of different types of sensors on there, but then the cost goes up. So the real holy grail is you've got really, really clever software that's using really cheap hardware and doing a much better job than cheap hardware alone can do. So, you know, there's actually a big part of the things I do myself, taking things like really cheap GPS sensors and supercharge them with software to make them much better. And that's how we need to solve this problem. Much more smart software and lots of cheap different types of hardware.
Well, we'll have to see. We'll have to go and see how that develops over the next few months then, because unfortunately there have been a couple of these high-profile crashes. One of the other things that we saw with Tesla that we covered last month was that the autopilot system that it has at the moment can be tricked into operating without a driver in the driver's seat. So at the moment, autonomous vehicles are in this something like level 2. You'll know the levels better, where they can drive autonomously in a lane, keeping at a certain speed, below a certain speed, but somebody has to be ready to take over if there's a glitch or a problem with the system. And what we were seeing last month, and some reports had shown, was that Tesla's autopilot system could be very easily tricked into believing that there was somebody in the driver's seat just by hanging a chain on the steering wheel or other simplistic tricks. So it looks like they took up your suggestion from last month, and they now seem to be putting or sticking a camera in, or a more powerful camera into the car just above the rear view mirror to actually check that people are paying attention. Do you think that's a worthwhile fix to this problem?
Yeah, and in fact, I do recall something about maybe actually that it's because people are intending to legislate that you have to have that.
Yeah.
So that might be why Tesla might be being forced to do it in order to satisfy some legislation that's coming in. But yeah, as we discussed last time, same as the external sensing kind of issues where you actually want lots of cheap different ways of sensing what's going on. The smartest thing is to just make it so complicated for someone to try and trick the system, they just don't bother. So weight sensing on the seat, plus sensing that there's body heat in the seat, plus detecting that there's a pair of eyes there that are open and there's a face and all that kind of stuff. And you make it so difficult for someone to fake a human being in the driver's seat, they just won't bother.
But it's just not worth it. There's a difference, isn't there, between being able to trick it by hanging an orange off the steering wheel and having to break into a morgue, get a warm cadaver and stick it in the driver's seat to be, it becomes not worth doing. I'm taking it a little bit far there, but getting a ballistics gel torso to be able to do this, it's trying to make it as unappealing as possible to bother doing this thing.
Yeah, exactly. You got to make it much too hard to be worth bothering
To be worth it's kind of banterous if you have to stick an orange on the steering wheel, and it's not so much fun if you have to go to great lengths to do it. So that sounds like a positive move forward. Another thing that was just to sort of clean up the ones from last time, the Ingenuity Mars helicopter, it'd been having a few problems. So there'd been a few failures to launch correctly, a couple of missed flights, and it now seems that on their sixth flight is the first one where they've actually had a problem where the helicopter was struggling to keep the right trajectory and to keep aligned with respect to the surface of Mars. What was going on there?
Yeah, so what the helicopter does is it uses accelerometers and gyroscopes to have an understanding of its tilt and its motion, and it has a downward-looking camera.
Yeah,
and it compares the information that it can see on, here's a pattern of rocks in this frame, and then a hundredth of a second later or something, the rocks have moved to here in the camera view. So we think we've moved down a bit. What do the accelerometers and gyros say? Okay, does everything agree? Because if you just accumulate measurements from an accelerometer and a gyroscope, eventually you get completely confused as to which way up you are and where you're pointing. You need to keep getting some external reference, like how rocks in the scene are moving and which way your kind of path is going over static objects. And what happened was they lost a frame from the video feed, and not only did they lose the frame, but they then mistimed the frames that all followed. So in effect, the camera feed suddenly was out of synchronization with the inertial sensors, which shouldn't have been possible. And the way the code should have been built, that simply should not have ever occurred. And you can test for things like this so that they can't occur. And so it's very unlikely that have sent such a poorly written piece of code up to Mars. It's much more likely that the problem we've been talking about had occurred, where the computer was hit by a cosmic ray particle that disrupted some aspect of the program running in memory and caused a glitch, probably effectively corrupted or deleted the data as it was being processed, and then made everything fall out of synchronization. So for people who didn't watch last time, the helicopter actually just has basically a smartphone inside it, normal smartphone technology, not the usual radiation hardened technology that you send to Mars for the normal rovers. So they're kind of testing out if they can use low cost but high power, simpler components on Mars. And what they're finding out is it's risky, which is what we expect, because if you bash electronics with cosmic ray particles, then you corrupt the code that they're running.
So they're finding out that half the time you can get away with it, and most of the time you can't. So it seems roughly, I don't know, how many flights have they had now? 6. 2 of them were called off, and one of them has been a little bit hair-raising. So it seems like half of the time something goes wrong, even on these short flights. So obviously, if you want to run these things for longer periods, you're gonna run into this problem more often than not. So
they have said as well that they do intend to just play with this thing until they break it.
Yeah.
So, they will just push it to the limits until it's in bits, as far as they've said.
That always seems to be the sort of modus operandi with these rovers, doesn't it? They have a set window that they want to do their physics analysis or expect the thing to be able to run, and then they just run it into the ground afterwards to see what extra information they can get. I guess with this, you sort of mentioned last time, they're thinking about having one of these things to scout ahead, see the terrain. Is there a big crater there? Is there a big pit of sand there? Because then the rover or future rovers will be able to move forward more speedily over safe terrain. So I guess that's the idea, what they're trying to get with the Ingenuity helicopter. The only other thing that came up from last time, we talked about AirTags. These AirTags being essentially a new little product from Apple, which you can stick on something. If it goes missing, you can get a signal from it back to your phone through essentially the environment of Apple products that are out there in the ether. And it seems that as soon as we discussed this, one of them had been hacked by, the worldwide hacking community, I guess. What's happened there? Who's broken the AirTags, and how have they done that?
Yeah, this was incredibly clever as well. So basically, whenever people like Apple generate these very clever products that we go on to use, they put them out into the world in a very locked down manner, as much as possible, so that they just do the job they're supposed to do well, and they can't be fiddled with and broken and hacked and stuff. And what this security researcher had exploited is he or she, I think it's a guy actually, he gambled that certain lines of code had probably still been left in the production system. They'd just been set to off. And one of the classic things about writing software is that you need to debug it, which means you need to be able to run analysis on it and change it on the fly and make improvements to fix any problems that are in there. And all of these platforms generally have debugging modes where you can fiddle with the insides to your heart's content, but you turn all of the debugging modes off, or ideally completely remove the ability to have a debugging mode when you put it into the world. But this researcher gambled to some degree that what Apple might have done was simply had a line of code that said,
don't run the debugger. Yeah,
if debugging flag is true, allow debugger, else, go on. And so there was still, he sort of gambled that within the code that runs inside any AirTag, the debugging mode was just being skipped over every time you turned it on. And so
I guess that's sort of like what happens in your PC, right? You can click a certain button combination to go into the sort of root debugger of your computer and do all sorts of things that I don't really understand what's going on, but sometimes smart people do that to fix my computer.
You're absolutely right. Often if you press a key fast enough early on, you get a special menu. Yeah. Exactly. And there is no way of pressing keys on the AirTag, right? So there's no obvious way of trying to do that. But this approach was, let's assume that the line of code is in there. So how do we force it to skip over a line of code is the logic. And the way that the attacker did this was you kind of power up the AirTag. So you put the battery voltage on, so the electronics start running. And the logic behind the attack is, if you dip the power just for a moment and then put it high again, then as the CPU is trying to execute the lines of code, if you dip the power and bring it back up, it won't properly execute the line of code it was on, because you're not powering it at that moment, and it doesn't execute it properly, and then bring power back on, and you've skipped that line of code. That was the
very sort of brute force hardware approach.
This whole thing is like modern day Turing, Bletchley code breaking stuff. It's such a clever approach to solving such a difficult problem. But so what the guy had no idea whether this line of code existed, where it was, when it actually would get fired. And so basically, he brute forced it. He tried every possible timing offset from powering it up. So 1 millisecond, dip the power. No, then next time try 2 milliseconds. Next time try 3 milliseconds. And he just tried a huge amount of options as to when he might dip power and which lines of code he might skip. And loads of times the AirTag probably just did nothing through this attack. But sure enough, there was one particular delay and then power dip and then power when he would have skipped this line of code successfully, and he managed to put his AirTag into a debugging mode. Once he was in the debugging mode, he could read things off it and put things on it and install new things on there. And the little thing he showed off was that he changed the code that all AirTags are transmitting over Bluetooth. That's kind of the hello, here's my ID code, which is the kind of one job an AirTag is out doing. It's transmitting to the world, hello, I'm an AirTag and this is my ID. Once he'd got the debug capabilities, he could go and change that. And he changed it so that the AirTag was sending the URL of the YouTube video of Rick Astley singing.
So you get rickrolled by the
hold your phone over his AirTag, it fires up YouTube and you get rickrolled.
So what's so that's obviously quite amusing. The big concern with AirTags was that they're going to be able to give away your location. People are going to be able to stalk you around. What are there any implications of that with this hack, or is it just he managed to break it a little bit and it's kind of intriguing, but it's not really a big concern for security and safety of this product going forward?
So certainly historically, Apple have been very good at responding very quickly to things like this. In my own field, there was an event at a conference I was at where iPhones got bricked, they got broken because someone was spoofing the GPS in a conference center, and it actually affected the iPhones, and they fixed the problem very, very quickly, and the iPhones were not susceptible to that anymore. And I'm sure that they've paid attention to this, and they will fix this problem. So they'll make it, now that this has been publicly released, iTags will be more secure in the next version, I'm sure. I'll just correct one thing you said. You said something about people, AirTags sort of transmitting GPS, or people being able to track people with them. They simply say, hello, here's my ID. And that's all they do. And any ability to track an AirTag is because your phone or someone else's phone, which has location capabilities, can hear and talk to that AirTag. And so the phone just says, I am at this location using my GPS chip, and I found an AirTag that's nearby. So the AirTags themselves don't have GPS in them, and they can't kind of transmit any coordinates out. They just say, hello, here's my unique ID. There have been concerns about whether people could use AirTags for stalking and to put an AirTag on something and then track it and follow it. And Apple have stated that they have some mechanisms in place to try to prevent that from being a problem. But it has been published. People have shown that you can, put an AirTag on a parcel, ship the parcel, and then track it through its entire journey over many days, which some people find a very useful feature, and others might not, be too happy about the ability to kind of track things cheaply. But this particular attack of changing the ID, it's difficult to think of anything immediately malicious other than
having to listen to that damn song again.
Well, the exact attack is obviously just to rickroll people. I mean, in theory, it means that you could take someone's AirTag and change its ID, potentially without them knowing.
Yeah.
But it's more likely that if you wanted to stop someone from being able to track an AirTag, you'd probably just smack it with a hammer.
Yeah.
So there are cheaper, more efficient ways to stop an AirTag from working properly than this complicated attack.
So it probably seems like a cool little thing, but probably not desperately important for the future of this product. Sorry for anyone who was watching, by the way, when the first one I could find link for this hacking of AirTags was Mail Online, which has so many ads that it seemed to make the stream have a mild seizure for like 5 seconds. But I think everything's back now. I mean, I don't even know how I would go about counting how many ads have popped out of this page already. But okay, good. So those are the topics from last time. Moving on to sort of what's been going on this month. So the first one I wanted to discuss with you was this idea of a moon-based sat-nav or moon-based telecoms network. So ESA, the European Space Agency, have been pushing this idea of having a moon-based GPS. And it seems like the main idea with this is not actually to track things on the surface, although that would be possible to some extent, but to track the position of rockets essentially going from the moon, from the Earth to the moon. What's going on here, and how would this system operate? Why do we need it?
So there's clearly some greater plans to keep expanding our reach into the solar system. Elon Musk is talking about trying to put people on Mars. That the moon is a stopping off point to other planets in the solar system, and people talk about trying to extract minerals from the moon. So the only reason that you would do this is because of some larger plan for more serious deployments of of people and objects on the moon. There's no point doing this just for lobbing a rover on the moon every couple of years. So
which is one of the things they mentioned in the article, is that rovers could move around quicker if they had more precise positioning and this kind of thing. Seems a little bit much to do when you could probably have a rover that had its own cameras and its own sensors, like we see with Perseverance on Mars.
Yeah, I don't really buy that statement, in the sense that if you're going to put a small number of devices into a remote location, the cheapest thing to do is put on that small number of devices some relatively expensive, clever onboard navigation capabilities, really good cameras, clever software that's processing and determining your location relative to objects around you, plus the top-down imagery you have of the area you're in. We have imagery of the whole of the moon down to a resolution of a meter or something. So those maps, those top-down maps, plus cameras on the rover, are enough for you to understand where you are to a high enough precision to kind of navigate around and say, I found an interesting rock at this location on the moon. The only reason to spend a lot of money putting a navigation and communication system orbiting the entire moon is that you're going to have such a large number of devices on the moon that what I said first isn't cost effective. So the GPS chips in our phones cost about $1. The entire constellation of satellites we have orbiting the Earth, plus the ground stations that look after them and so on, costs billions of dollars. Yeah. But there are billions of GPS chips. Yeah. So it makes sense. Whereas you wouldn't spend a huge amount of money putting an entire satellite-based positioning system in place just for a handful of devices on the surface. And if you wanted good radio-based positioning for a certain area, it's still cheaper to set up a local network. So you'd basically build some towers around the area that you're particularly interested in. You might have 4 towers in a square 50 meters off the surface, covering dozens of square kilometers of the area where you have your base and your mining or whatever it is they might be thinking of trying to extract from the moon. So it's an interesting idea that they're talking about here. I'm skeptical as to how much they need it, unless they're planning on putting dozens, if not hundreds, of moving things on the moon.
Well, they said a large flotilla of lunar missions over the next decade, including essentially the sort of child of Apollo, which will be called Artemis now. On the artwork, it looks like they're planning to have some sort of habitation there. You talked about it being very useful for mining resources. So when we're thinking about moving towards Mars, the ability to harvest water, for example, from the surface would be very useful. The ability to make fuel, for example, would be very useful. The moon being far lower in gravity would mean that you wouldn't have to lug all of the fuel off the Earth. And I think there was some ridiculous statement like 90% of rockets are the fuel, or 95% of rockets are the fuel. So if you can get to the moon as a sort of pit stop, it could be a very useful way of going forward. But how would that system work? So you're saying it would be better to have some masts. So those masts would what? Take a signal from the Earth and then triangulate your position relative to those masts? Or how would that system work, rather than having a whole GPS network around the moon, which seems like a little bit far-fetched?
Yeah. So the benefit of using satellite-based positioning is that you can construct the orbits of the satellites so that you've got coverage of the entire planet. So there's positioning capabilities absolutely everywhere. But
that presumably requires a reasonable number of satellites. I think we have like 100 around the Earth at the moment, don't we?
Yeah, so the magic number on the Earth is 24 satellites in just the right positions, orbiting in just the right way to give you almost 100% coverage of the whole planet. And that's per constellation. We have 4 constellations for USA, Russia, China, and the EU. So yeah, we have over 100 satellites, positioning satellites over the Earth. So depending on exactly what orbits they use for the moon and various various things. That number might be greater or smaller than 24. But to do positioning of this type, you need to first know very accurately where the satellite is, because you work out where you are relative to them. So if you only know where they are to 100 meters, you're only going to know where you are to worse than that. And nothing is ever perfectly stable in its orbit for lots of complicated reasons. Even though GPS satellites are 20,000 kilometers above the surface of the Earth, believe it or not, 20,000 kilometers up, there's still atmospheric drag. And there's heating and cooling effects when they move around and go from sunlight to shadow and things like this. So just because you first kick off that satellite into orbit around the moon doesn't mean that you'll always be able to know exactly, accurately, perfectly where it is just from giving it its first initial kick. So they'd have to keep monitoring where those satellites were around the moon too, doing that most likely with ground stations in known locations on the moon, which is exactly how it works on Earth. We're not really positioning ourselves relative to the satellites when we get a GPS fix on Earth. Really, you're positioning yourself relative to about 6, I think it is, ground stations around the Earth. The ground stations are telling the satellites where they are, and then the satellites are how you work out where you are.
Because it's giving you that line of sight instead of going straight from the ground station to you.
So
the ground station tells the satellite where it is,
yes.
and the satellite tells you where you are, but it goes up and down back to you rather than just straight from the ground station to you, I guess, because it can't go through the Earth or it doesn't have direct line of sight to you.
So on the Earth, a GPS receiver just listens to the messages from the satellites, and in the message is information on where the satellite is. So from the content of the message, you calculate where you are relative to the satellite. How does the satellite know where it is? The ground station tells it where it is. So, but it's not like the message that you use comes from the ground station to the satellite. It's not quite like that.
Okay.
But the getting back to this thing about local static things versus orbiting things on the moon, the cost and complexity of setting up an entire orbiting satellite-based positioning system on the moon is very high compared to installing some masts on the Earth that just cover the large area you're particularly interested in. So if you scroll up a little bit to this habitation module, assuming that this is what they're aiming to do, those people and that rover there, they're not going to be toddling around the entire surface of the moon from this habitation module. They might only ever move, at most 100 kilometers from this thing. And you could set up a few static masts, a small number of them, and serve this entire region using tall masts transmitting radio signals for positioning, and effectively, provide similar performance. But it's much cheaper to do that because, by definition, those static masts never move, unlike the satellites, and therefore you're not constantly pumping lots of money into having a way of constantly confirming where the source of the transmission is, which is what happens when you're orbiting satellites. Plus, satellites always need replacing; none of them last forever. Whereas static masts on the Earth need much less maintenance, and it costs much less to maintain them. So
this seems like it's maybe a bit more fanciful than perhaps is being suggested, or maybe far more targeted towards just this positioning of things as they move towards the moon rather than on the moon's surface specifically.
It's interesting to go straight from we've got a few rovers on the moon to we're going to set up a satellite-based telecommunications network. You normally go through why don't we start with some Wi-Fi beacons, statically first. You normally kind of stage up through a local network and then have, I keep wanting to say global. Yeah, global still works for the moon, doesn't it? Lunar coverage. There you go. Full lunar coverage.
So, naive question, and we have discussed this a little bit offline, but probably worth going over for people who haven't been in those discussions. Why can't we just use the Earth-based system? Presumably you've got a large number of satellites there. If they can point at a particular place where you want to put your base, you put it pointing towards the Earth. your base. Why can't we just use the Earth-based system to do some decent level of positioning on the moon?
So, and this picture you've got up is a lovely place to refer to it. So you can see that the Earth itself,
almost like it was planned that way.
You can. I'm not sure how perfectly to scale or not that might
No.
be, but assume is roughly right. So the Earth there, as seen from the moon, is subtending an angle of a few degrees, basically in the sky. And what you can't see is the GPS constellation, which is roughly twice as big.
Yeah.
So the
bigger circle.
Thank you very much. Yeah. So the Earth itself has a radius of 6,500 kilometers, and the satellites are orbiting at about 30,000 kilometers from the center of the Earth, something like that. And you have this issue in positioning called dilution of precision. Basically, what you want is, if you're going to try and work out where something is, and you're going to do it at range and making some measurements, either angles out from a point or ranging measurements out from a point, what you want to do is you want to look at the object from as many different angles as you can. And that gives you the most accurate way of working out where it is. If you're only able to make measurements from roughly the same location, a very small angle that you can make measurements from, you get a very, very poor positioning estimate, what's called a poor dilution of precision. And so this very same GPS constellation, which we can use on Earth to work out where something is to a few meters, you can only work out where something is on the moon to a few hundred meters because of this issue.
Probably a nice little picture here that sort of shows you the issue in C here, that if the signals are all coming sort of from the same line, so you can imagine there's a line going through through the red and the blue satellites here, the overlap at your target that you're trying to range is very, very large, so it's very difficult to work out where they are. Whereas if you have signals coming from different directions, as in B, you can see that area of overlap between those signals, those two ranging measurements, is much smaller. So if you have satellites coming from all different directions, sending signals from all different directions, as we do on the Earth, you can get very precise GPS positioning. But if they're all coming from the same direction pretty much as the moon sees the Earth, then you get this horrible sloshing out of that precision.
Just so that you're so that our listeners are not confused, the red and the blue circles there are not representing like the Earth and the moon.
No.
They're representing two satellites that are transmitting a pulse that you're using to work out where you are. And so in B, it's showing that if you are at the green square, then you've got the signal from the red satellite coming from one side of you, and the signal from the blue satellite coming from a completely different side of you. And where those arcs of time from the two satellites cross, you've got this green square overlapping. You're somewhere in that green square. But in C, if the blue satellite and the red satellite are in the same place in the sky relative to you, they're in a line that you're the other side of, then those measurements from the satellites will be overlapping in that much larger green sort of, what kind of shape are we calling that? Crescent.
Yeah. So you get so you can only say you're somewhere within that much larger crescent now. So the geometry of the system really impacts on the precision that you can get. So you would need dedicated positioning systems, whether those be masts, whether it be GPS, at the moon to get high precision measurements of positioning. You can't simply use the Earth-based system. And I'm going to do a calculation. We've been sort of working on it to work out how precise your sat nav in your car would be if you took it to the moon and started driving around. And I think we've got that it's 200 or 300 meters at best. So when it says turn left at the next crater, you're probably already at the bottom of the crater. So watch out for that video. Hopefully get that out over the weekend. So that's Moonbased GPS. The other thing that came out sort of this week that you sent me was the Chinese artificial sun. So fusion power is sort of the great hope for, infinite clean energy coming down the pipe. Obviously, You can use hydrogen, fuse hydrogen together. You can get the hydrogen from seawater. So you have this essentially limitless supply of clean energy. And the product produces a lot of energy and helium, which is obviously much cleaner than fossil fuels. So there's great interest in fusion. And the Chinese, apparently, according to Chinese state media, so no comment on the accuracy of this, but let's take it as read, says that they've set a new world record for having an artificial sun. So what they've done is they have this essentially plasma accelerator, and they've got a fusion reactor going, essentially a mini sun in the heart of this reactor, and kept it going for what is it here? What did they? 100 seconds. So 1 minute 40 seconds at a temperature of 160 million Celsius. So this is a new record which surpasses the last one, which was from I believe it's in here somewhere, Korea's K-Star reactor, which was 100 million C for 20 seconds. So a good step up and a good movement forward for fusion. Now, obviously, the sort of pathway for this is that you'd want this thing to run almost continuously. So a lot of people who are, because if you want to put power onto the grid, you're going to have it switch on, switch off, when demand is needed. But this seems like a good step forward in the field of fusion reactors. Do you have any thoughts on this story?
So I mean, this one's firmly your area of expertise with your all your time.
The old particle physics.
Particles into each other. So why don't you? It's probably useful for you to let people know what is actually going on with fusion. So with fission, you've got a very, very, very heavy, unstable atom that breaks into two smaller atoms, and when it breaks apart, it releases heat, and we can use that heat to generate steam to turn turbines, and that's how current nuclear reactors work. So fusion is smacking hydrogen or other light elements together to make them fuse into a heavier element.
Yeah.
So what you have very strong magnetic fields to try and hold it all together, and you're basically trying to crush lots of light stuff together instead of allowing lots of heavy stuff to blow itself apart. Is that right? But when you're crushing the light stuff together, how are you getting energy out and making electricity then?
So the big problem with fusion, as you say, we're trying to fuse, where the name comes from, two smaller elements together to make a bigger nucleus. So we take tritium and deuterium, I believe they take, which are two isotopes of hydrogen, so essentially heavier hydrogen with more neutrons, and they want to smash these nuclei together to make them fuse together into a bigger blob, a bigger nucleus, which is helium. Now, this is really difficult in the first instance because you have two positively charged nuclei. So there's a Coulomb barrier there. They don't want to be together. There's two positive charges. So you have to put a lot of energy in to make this happen. Very strong magnetic fields, very high temperatures to overcome that Coulomb barrier. But
sun sorts this out using gravity, right? So
yes.
All of the stars, there's loads and loads and loads of really light atoms, mainly hydrogen. They're all pulling themselves together under gravity, and gravity is smashing these light particles, these very light particles, together to make heavier ones, and that releases heat. Is that right?
Yeah, but obviously in the core,
using gravity here.
Yes. So in this case, we can't use gravity because we don't want to make a whole sun of, what is it, 10 to the 30 kilograms or whatever.
They just can't.
Yeah.
Anyway.
Yes.
Conversation.
Good point. So instead, you use very, very strong magnetic fields. In fact, the plasma that they make, and you were asking about this yesterday, it's very, very thin, very, very low density. So it has about the same density as the atmosphere in the mesosphere, so very much up at the top of the atmosphere. So very, very low density. But
so the mesosphere is the highest level of our atmosphere or something, is it?
I believe so. I would have to get... I'm not an atmospheric scientist, so let's see where the mesosphere is. Might be where the Red Bull guy jumped from.
It's not one I know, so I think it's probably beyond where we have satellites knocking about.
Mesosphere is up here,
that
above the stratosphere. So
85 kilometers, is it?
Yeah, it looks like it. So
that's quite far out. Yeah,
so a decent way up. So very, very thin. And the way we get over that problem that you were mentioning, where there's no gravity to sort of smash it together, is with these very, very strong magnetic fields and very, very high temperatures. So the temperature in these fusion reactors is 10 times that of the core of the sun to overcome.
They make in the fusion reactor, they're making the very high temperature. That's then the particles have huge amounts of energy.
Yeah.
So the hot and fast are the same thing for particles, right?
Correct.
So the faster you're making a particle move, effectively the hotter it is.
Yeah.
So they have that incredibly hot. These very light small particles are therefore whizzing around crazy fast, so they can hit each other so hard that they fuse.
That it overcomes that initial want to push apart. Yeah.
So then you're trying to repel each other because they've got the same charge, but throw them at each other fast enough and you can get
over that if you give them enough energy. And then
are the magnetic fields just to stop them flying out the other end?
Yes, I guess, because if you don't have a strong magnetic field to guide around the corners, you just essentially have a beam that fires off into space, right?
So the strong magnetic fields are basically making these super fast particles keep
going around the system. So you can imagine in a particle accelerator, the reason we have them in a circular shape, right, is there's a lot of reasons, but one of the reasons is you keep getting chances to interact, right? You keep whizzing them around. Eventually they're going to hit something. Come on, hit. And they're going around the speed of light, so you're getting millions of trials every single second. So it keeps them going around the system. Eventually they're going to smack into something. And the way we get energy out of this, which is, the whole point of doing this, is that once they fuse, the nucleus that is produced, the helium nucleus, is actually lighter than the reactants that went into producing it. So if you were to add up the mass of the nucleus of the deuterium and the tritium, then they are heavier than the nucleus that gets produced, the nucleus of the helium. And you might think, well, how does that work? Mass can't disappear. In chemistry, we learn GCSE, the mass is conserved. Not in physics and not in relativistic physics. So that mass can change and be converted into energy. And that difference in mass between the masses of the nuclei, which is very small in absolute terms, becomes a very large amount of energy released because it gets times by the speed of light squared. So E equals mc squared. So a very tiny difference in mass of the nuclei can give a very large amount of energy. So it's that fusing together of the nuclei to give a smaller nucleus that releases a hell of a lot of energy. And I did a quick calculation, actually. I should have had this open already. It's on my tutor page.
So is the idea that they have to heat the thing up to a certain level just to get it going, but once it gets going, the hope is that it itself starts getting hotter and hotter and hotter all on its own as it uses up the particles you provided to it, and so they'll tap off extra heat and use that heat to heat water and make steam.
Yes, I believe so. I believe it'll be sort of very similar. I'm not exactly sure on the designs to move this forward to a power station, but I'm guessing that heat will then be tapped off and used in a semi-standard way that we have now to heat steam, and then the steam drives some sort of turbine, and then you get the standard electricity production. So the time scale for this, or the sort of roadmap for fusion, I think I had it up before somewhere. Here it is. The roadmap for fusion is to sort of have these, understand how to do this sort of fusion, actually get it working, get it going for a longer amount of time, which we're sort of moving towards now. And then we have this ITER experiment, which is coming online, I think, in the next 5-10 years, to understand this even better. And then moving towards this demo, which is essentially the design of a power station that uses this process, which I believe seems to be at minimum 20 years off into the future, which always seems to be the issue with fusion. So at the moment, the state in fusion is very much understanding the plasma. Can we diagnose what's going on? Can we understand the energy that's coming out? Can we keep it stable for a decent length of time? What's the magnetic field we need? What's the temperature we need? And there hasn't really been much exploration, as I understand it, of actually getting useful energy out of these things. So when I had a chat with my friend who's a fusion expert, and I was giving the usual question, which is, well, you never seem to get any energy out of these things. It costs more energy putting in than you get out, so what's the point? his sort of pushback, and obviously this is slightly biased because he works in the field, was that, well, we haven't really tried yet because we haven't been trying to get useful energy out of this thing, because why would we bother? That was never the point. We've been trying to understand how to keep these, how to get this fusion working and the plasma stable. And then what was the point of having a steam turbine on the end, because we're not going to use it for anything. It's later down the line that this sort of trying to get useful energy out will occur. So maybe that sort of accusation that they never get any energy out isn't quite fair, because they've not really tried to do it yet.
And what is it that is limiting them to like 20 seconds, 100 seconds? Is it that as they build up more of the newer, heavier particles, the settings for the magnetic fields need to change to keep everything well behaved? And because it's all getting complicated in there and changing state, the plasma just ends up whacking the side of the container, or no longer being contained by the magnetic field.
That's a very good question, actually. I'm not sure I could give you a definitive answer on that, but it certainly makes sense that you would have to run this at an extremely high temperature, which means very, very high energy inputs. And as you say, the system is going to be changing all the time. I can imagine if you're putting even more heating, I imagine it's going to expand and become more difficult to control as you get even more heat. And I imagine at the sight of any sort of energy fluctuation or size fluctuation, they're pretty quick to shut this damn thing down, because essentially it's a massive bomb.
Do you think it's the electricity bill? It's like the number of coins that were in the meter.
They are not put enough in now.
But did for 20 seconds, and China managed to scrape together enough for 100 seconds before like the whole city just ran out of power.
I honestly, it probably wouldn't surprise me, but I imagine, speaking as intelligently as I can, that it's what you're saying, that it's difficult. So my friend works in essentially plasma diagnostics and trying to understand how these plasmas behave. And I imagine it becomes unstable or dangerous. And you need to understand the magnetic fields that you would need to apply, the confinement protocols you would need to apply to be able to proceed with more safety. I don't know if the fact that they're whizzing ahead in China means that those protocols are a little bit more lax. I don't want to say that. But maybe. I don't know.
I don't think we're getting brave enough on our live chats yet.
No. Exactly. So I don't
say to do totally off the cuff order of magnitude calculations, but we should calculate how much it would cost with, like, you know, a standard 3-bar electric fire to do 100 million degrees C for 100 seconds, because they probably are quite expensive experiments.
I'd imagine that. Yeah, I'd imagine it's not too cheap. I did
it's not really heating stuff up to that temperature, though, is it? It's that they accelerate the plasma up to a speed that represents those temperatures, is it not?
Yeah, basically.
So it's not like, if you go back to the picture of the thing with the picture of the actual experiment. So yeah, it's not like that thing is actually cooking away at 100 million degrees C and everyone's kind of getting warm. It just
means that the particles are whizzing around very, very, very fast.
Yeah. And did you know how big that thing is? Obviously just all of the plumbing to get it going. Is the plasma like the size of a cricket ball, the size of a grain of sand?
So I think inside it's confined to probably a foot across. I don't think it's filling the entire container. So I imagine it's on sort of that scale, because what is this? This looks like sort of 6-7 feet tall or something, and I imagine they don't use most of that. So you're talking half a meter or something inside, probably, where they're doing the fun stuff.
Yeah.
If I'm making an educated guess. But you asked a question the other day, was what would happen if you threw a sandwich into this thing? Now,
yeah, could we use it to toast some bread? Was one of my first questions when we were first chatting about this.
Now, my first reaction to that was, well, it's just going to plasmarize it, isn't it, straight away? But then when you step back and think about it, if it's got this very thin density of plasma, I imagine what would actually happen is that you throw it in, and, you know, obviously it's going to probably trigger some horrendous safety that turns everything off. But apart from that, it's probably not going to get hit by that much stuff, right? So I imagine bits of it get charred, but it just flops through in kind of a boring way rather than becoming part of the plasma stream.
Yeah, we don't cause a catastrophic, massive explosion.
No,
by chucking in a bit of Hovis.
I think it'd just be really disappointing.
So yeah, I think that's probably what it. So you know the piezoelectric clickers that you can use to like click a gas fire with, right? I mean that's a tiny little spark, which is plasma. That's you're watching the blue spark of like nitrogen plasma being created. A lightning bolt is hotter than the sun, right?
Yeah.
So you've got this tiny little lightning bolts that you're clicking every time you start a gas fire. You're generating a huge amount of temperature in a tiny little space. But you'd never be able to toast bread like that, would you?
Yeah.
And I think it's the same kind of thing. I think it sounds cool and it looks cool, but actually there's probably an unbelievably tiny amount of actual usable energy in there. And what sounds really amazing, 100 million degrees C, is actually
really confined onto some tiny little
gas moving very quickly, which is not quite the same as being able to cook bread with it.
I told you the really disappointing experience I had at the LHC, didn't I? So we went to the start of the LHC, and you're thinking, oh, this is going to be amazing. It's like So
that's the Large Hadron Collider in CERN.
The Large Hadron Collider at CERN, yeah.
HD with you.
Yeah.
So the big particle accelerator in Switzerland.
Yes. So marching to the start of the experiment, feeling like I'm off to find, the starting of the Nile, great historical navigation, and you get there, and I'm expecting some amazing, huge machine that sort of gets the hydrogen going around, and all it is a bottle of hydrogen on a wall that sort of goes, sss, and that's all the protons for a run of the LHC, because you've got to remember that in a sss from a hydrogen bottle are billions and billions and billions of protons, which is enough to fill up the machine. So it was a massive anticlimax, and I imagine that this is something similar where, yes, on the particle itself you have a great amount of energy for a tiny particle, but it doesn't take much energy to get that tiny microparticle up to a huge speed, which equates to a massive temperature. So in terms of the whole energy that's in the system, it's not like having the sun in the room. It's having a tiny part of the sun in the room, which is very much confined to a small space. I mean, if you do the calculation, you can take the mass of the nucleus for tritium, deuterium, and then the neutron and the helium that get produced in atomic units. And if you do the mass difference, times it up by c squared, you get a tiny amount of energy for each of these interactions, 3 times 10 to the minus 12 joules. So, if you're thinking of high school physics, usually it's a few hundred joules for, dragging a kilogram weight a few meters or whatever it might be. But what you've got to then remember is that there's so many of these particles within even a small amount of tritium or deuterium. So if you were to take a litre, for example, of tritium, and you probably got about 10 to the 22 particles. So once you start timesing that up to be a reasonable amount of material, you then start to get large amounts of energy. So to get reasonable amounts of energy out, you have to have a reasonable sized plasma beam, as you say. So I estimate that from a cup or a litre of deuterium, you could get about 300,000 joules, which is enough apparently to, 7.5 times 10 to the 10 joules, which is enough to boil about 250,000 kettles. So this is the great hope with fusion, is that from this small amount of material, this heavy hydrogen, you could get a hell of a lot of energy. But it's understanding, as we've seen, how these plasmas work, getting them running for a decent amount of time in a safe manner, which is the big problem. There's limitless untapped energy there. It's just getting it out in a safe and technologically feasible manner.
Yeah, I mean, that's the thing that would be really interesting to look into, because the way a nuclear fission reactor works is you just basically have your radioactive heavy elements sitting in water. They're breaking down, and the particles that are being created in a fast are basically heating up the water, and you've got hot radioactive water, and that hot radioactive water can be used to turn turbines. But you can't see the obvious next step of being able to heat water using plasma that's inside a magnetic field in a system that's so delicate that if you chuck in a piece of lead, it breaks.
Exactly, which is why, you know, there's a lot of people who say at the moment it's not right to be pushing fusion as this great solution to the environmental crisis, because we haven't even started to understand how to run these things for minutes yet, never mind hours, days. So when everyone comes home and clicks their kettle at the end of the day, you want to be able to turn one of these things on and run it for an hour, 2 hours or whatever to generate the power that's needed for that demand. And we haven't even started to think about that yet, I don't believe. I mean, I'm sure some people have started to think about it, but we don't know how to do it. And that's this great hope with this ITER experiment that will start to analyze and model these plasmas and then be able to put them into essentially, you know, energy production environments and similar. But as ever, I mean, I've been looking at this for 20 years since in physics, and it always seems to be the same distance off into the future, if not longer. So I don't think this is going to be, unfortunately, going to be the great savior on climate change. Probably looking at, I don't know, 30, 40, 50 years off into the future where this is going to be any sort of mainstream energy production.
And I highly recommend for your listeners Dave Mackay's book, Sustainable Energy Without the Hot Air. Sadly, Dave Mackay is no longer with us, but he was a phenomenally clever professor at Cambridge. He probably lectured you as well, I imagine.
I think at some point we had him. I can't remember what course it was for.
Well, we're keeping his order of magnitude ideas alive with all this stuff. Actually, he was a great man for, and in fact, the book is full of them. Lots of simple ways of answering questions like, is fusion right? Is wind power correct? Is it going to be solar? So if you've not read it, Sam, I'd highly recommend it. I think you can find it for free on a website that is his old homepage. Sustainable Energy Without the Hot Air. It's really good.
And obviously the big benefit with this is that we don't have to deal with the horrible things that come out of a fission reactor. So out of a fission reactor come all these horrible things that are still radioactive. And then we have to, you know, dump them at the bottom of the Marianas Trench or wherever they go. So there's obviously still some resistance, or a lot of resistance, to traditional fission reactors, even with the sort of push on climate change. But we'd get rid of all these nasties as well and have a great energy source above and beyond uranium and plutonium, which would essentially just be seawater.
We can't just make little suns either. So, you know, there's well understood, very simple but impenetrable physics around the fact that you obviously need a certain minimal amount of matter for it to bind itself together from just gravity alone, which is an incredibly weak force. So you need so much stuff that this incredibly weak force, gravity, can actually be used to overcome this incredibly strong force, electrostatic repulsion, which is what's normally stopping these particles from getting close enough to fuse. And from vague memory, like, you need something slightly bigger than Jupiter. Like, Jupiter is almost getting on for being a big enough.
So what do they call it? A sort of brown dwarfy planet type thing, isn't it? It can't quite become a brown dwarf because it's not quite big enough.
Probably, thankfully, not quite big enough. I imagine that there's all sorts of interesting papers and studies looking into whether we would exist if certain things were ever so slightly different. And the fact that we have a moon that's used to drive tides, that has become a very important part of how life can move between the ocean and the land. That without the moon, we might not have evolved in the manner we have and stuff. But if there were two stars orbiting each other in our system, which is very common, binary systems are actually very, very common, because of the complications of lighting behaviors and tidal effects and other issues of the overall planetary dynamics, we might not have been able to evolve in our Goldilocks zone where water is liquid and stuff. So thankfully, Jupiter is merely a gas planet, not a little sun. But you need something bigger than we would need to go out into space and collect together enough material to be the kind of Jupiter-sized object in order to go and make ourselves a little sun and start playing with gravity-based fusion. So no point wondering about just cobbling together a little sun in your basement to do this all on your own using gravity.
So there's some really interesting designs actually with this. So the magnetic one is the tokamak, as they call it. So these donut shapes. I'll get a picture of one up. So tokamak. So usually they're these sort of donut shaped things. So you can imagine it's not a particularly nice picture. That one's a better picture, or maybe this one. So these donut shaped things where the plasma sort of whizzes around and it's confined into this sort of central area of the donut. But there's also some very interesting sort of piston based designs as well, where essentially what happens is you have these huge pistons, you have your reacting things in the middle, and then they just smash in and create a very tiny little area where they've been compacted into a very dense ball. There's some designs like that. Obviously that's not going to give you continuous energy, but could give you a big spike of energy. So there's all sorts of different designs for potentially doing this. I think there's various designs with lasers where essentially all the lasers converge and heat a small area to a very high temperature as well. Designs along those lines. But for getting a continuous stream of plasma and trying to keep things in a steady state, these tokamaks seem to be the way forward. So here's the sort of plasma whizzing around that donut shape. These seem to be the way to go forward, and this is going to be the way that this ITER experiment, which is going to run over the next sort of 10 years, is going to run, with these magnetic fields keeping everything in place, and then the plasma whizzing around. So I don't know. Again, with fusion, you just got to keep your eye on it and see how it goes. But as I say, it always seems to be 20 years off into the future. So
yeah, like autonomous cars.
Like autonomous cars, exactly. Always receding off into the future. So
to bring everything together. That's clearly the thing. Fusion autonomous cars. That'll be the
Mr. Fusion on the old DeLoreans. So as soon as you get that, we'll be away with the old autonomous vehicles. The final thing that sort of I noticed this month, and maybe we don't have to go into it too deeply, but was the China rover. So there's another rover on Mars, which is the Zhurong rover. I'm sure I'm butchering that name, but it means God of fire. So this is the apparently the first rover which has been put on Mars by a country outside of the US. So a very good and a very great achievement. I believe you said there's a little bit of an arbitrary sort of delineation there, isn't there? Because there's been a hell of a lot of things put on Mars. Maybe they're making rover a little bit of an arbitrary designation to say this is the only country that's never put something on Mars that isn't the US.
Well, I think ESA managed to smash a rover into Mars at a huge speed.
Okay, so maybe the delineation is that the thing walks away from the crash.
Any landing you can roll away from, is a successful one.
Yeah, there you go.
ExoMars, which is I worked on a navigation system design originally of what will be ExoMars when it finally launches. It's a bit late, but they tried a kind of ExoMars prototype test platform a few years ago, and it didn't survive entry. It's a really interesting example, actually, that the failures that have happened on Mars are all really, really interesting examples of how to be really careful with systems engineering, because they're all like the silliest little blunder of this team didn't speak to that team properly. One team was working in feet and the other team was working in meters, and they didn't realize this until the thing smashed into Mars. There's all sorts of interesting stories and silliness, but yes, if you don't include a crater with a rover in it as being a rover on Mars, then China are the second entity to get.
I remember the British, what was it? Was it Beagle 2 that
Beagle, yeah,
about 10 years ago, and there was a huge fanfare. Oh, Beagle's about to land on Mars, and then it just sort of disappeared from the news because apparently it just went in a crater or something, or didn't operate, and that was that. So there might be some other rovers on there, but they're non-responsive or didn't do the job that they were supposed to do. So this
a little while ago, it was only 50-50. Like the success rate was really poor, but we've been doing quite well in the recent ones. I think the ExoMars kind of prototype was the last one that crashed, and then we've had a good series of successes since then. And like you said earlier, when they do get them up there, they get really good ones up there. You've got Spirit and Opportunity on the slides there, so they were both designed to do 6-month missions, and they've lasted well. I think they're both still running. One of them is stuck and it's now a static platform. Pretty sure Spirit is still toddling around, and it must be 15 years now. So when they successfully land them, then they really make good use of them.
Yeah, I was going to say this is something that seems to happen regularly with these Mars missions. So we saw that they're going to run Ingenuity essentially into the ground. I think they what was the previous one to Perseverance? Was that the Curiosity, which they just ran forever?
Still going.
Yeah.
Curiosity was only a few years ago. That was the first one to use the sky crane, which was bonkers but worked, if you remember that.
And that's what they use this time, right?
Yeah, exactly. It's the only way to get the really big ones down there. Yeah.
So that one ran forever. This Zhurong one doesn't seem to have got much fanfare. I don't know if that's because it's the second one that landed sort of in the last few months, so it didn't get as much fanfare. Maybe it's because they were dumping debris all over the Maldives and people are a bit pissed at them. I don't know. Probably more simple explanation is just because it's not Western, so it's not as in our cultural wheelhouse, I guess. But that's on there. It's going to run for 90 days. It seems to be a little bit more of a simplistic rover, right? They seem to be a little bit behind where the Americans are. Maybe that's another reason why people have not really got so excited about it. It seems to be a bit more of a simplistic design.
I've not looked into it, to be brutally honest, so you'll probably have to lead, but I certainly can imagine they would start with your usual kind of remote control car-sized rover, as opposed to actual car-sized, which is what the Americans have got themselves up to through lots of successful landings. So I assume it's the more traditional approach where they probably used parachutes and balloons, like airbags, to basically get a lander down, and then
I think they actually did do the sky crane thing.
Really, they jumped straight to that.
I think they actually did. I could be wrong about that, but I got the sense that they did. Here it sits on its landing platform. Touchdown on Beijing. Maybe not. Maybe it was more an airbag. I'm not sure. I would have to check up on that. But I think what they've got is it's only going to run for 90 days. And it doesn't seem to have all the fancy sort of chemical analysis stuff that Perseverance does. So maybe it's more of a little bit of a proof of concept thing rather than being as advanced as as Perseverance. This model shows how Zhurong will descend from its landing platform. So it looks like it came off some sort of landing platform, but how that was delivered there, I'm not exactly sure. But yes, and it says in here that it is more like, I guess, some of the American rovers, Curiosity and then Perseverance, but not as much fanfare. And like I say, I guess it's because it's the second one to come along. I did wonder about, somebody asked me a question about getting these two things together, if they were to roll across. How you've worked on Mars rovers? How fast do they roll around on the surface of the planets?
So traditionally, when they, a non-autonomous smart one that's being controlled from the Earth crawls around at mere kind of centimeters per minute kind of speed, because the flight time's like 8 minutes, and you don't really want to suddenly realize that you're at the edge of a crater and then realize that minutes ago the thing toppled over into it. So you simply cannot really move that quickly as a remote control object.
Yeah.
So these things have to be autonomous and planning their routes and being given instructions to kind of travel short distances on their own. And one of the key things about ExoMars that I was working on was how to build into something with radiation hardened computers, in other words, very slow, simple computers, how to build in autonomy so that the thing can navigate successfully in real time and avoid objects and make sensible decisions about stopping and going and not falling down holes and stuff. So making them autonomous and making them clever enough to not crash into stuff all on their own is critical, because it's impossible to remote control drive something with an 8-minute lag in effect. So, and as we said earlier, this is why, Ingenuity is really interesting, because you can have a helicopter kind of scout out the planned route for the expensive bit containing all of the complicated heavy science equipment to then go to a certain area and do some expensive complicated science.
So if it's all simple and free and there's no boulders and craters in the way, it can just zip there and do whatever it needs to do, which saves you a lot of time and heartache on the mission. So it says, I've done a little bit of digging, and it says that the top speed for these rovers is about 0.016 kilometers per hour, apparently. So what would that be? 0.016. So that's 16 meters per hour. So that makes sense. 25 centimeters a minute or something like that.
It's like 15 centimeters per second.
15 per second. Yeah, sorry.
2 centimeters per second.
2 centimeters per second. Yeah? So yes. So about a meter a minute, something like that. Yeah. So about a meter a minute. And looking up the landing positions of your Zhurong and your Perseverance, which are these 2 points here, was apparently about where have I got it? I've got it in my notes here, which is about 1,000. Where is it? 2,000 kilometers apart. Apparently they are. So if you assume they both travel at this speed in a straight line towards one another, 7 years, unfortunately. 7 years for them to meet up. So that is not a thing that's going to happen. Not that it was ever suggested that it would be a thing, but it's not going to happen.
They could both last that long. It's just that's not the most important reason to send 2 rovers to Mars.
That's true.
So, and on this point, like the whole let's send people to Mars thing and stuff. Elon Musk is really keen on it and stuff, but I think it's a really bad idea. Just totally unnecessary to send humans to Mars. We should be concentrating on these robotic missions and actually improving what we can do with robots, because it's pretty much it's certainly a one-way mission with current technology, but it's these cosmic rays that are smacking the Ingenuity helicopter and corrupting its code and stuff. Basically going outside of the Earth's magnetic shield that we exist within is a really bad idea for human bodies. So there's the risk of basically turning up blind because of the cataracts you'll develop on the journey if your platform to simply move the humans to Mars over many months isn't well shielded enough. But you'd basically develop cancer while you're on Mars quite quickly, I think.
Also, I remember there was the survey. Was it a YouGov survey of would you go to Mars? YouGov survey. Would you go to Mars? to see how many people would actually be interested in going. I know there was the one for the moon. Maybe it's not. Would you go to Mars? Maybe they didn't. They definitely had the one for the moon, which was where half of the people couldn't be bothered going anyway. The question for the moon was, would you go to the moon if it was guaranteed safe? And only like 40% of people said they would go. And the main reason given was, no, I'm not interested. It's boring. I found ridiculous. The point I was going to make was with Mars, and I was saying this with my friend the other day. There was a lot of people who signed up for the call to go to Mars, to be the first people to go to Mars, which would be awesome, right? You'd be, oh, I was the first person or in the first set of people to go to Mars. But when you think about it, it's going to become very, very boring very, very quickly. I imagine the thrill of going there and the pioneering spirit of going there wears off pretty quickly when you get there and you realise it's just Nevada desert, basically, with nothing to do. So many ways that you could die.
Yeah. I love little plots like this one you've got here. So I want to know what the other option was. Like none of these add up to 100%. So was the third option like, I don't know,
let's
or I don't care?
Let's go
or was
into
it like,
what have we got?
Why are you asking me this stupid question?
So I guess the other one is, just piss off, mate. Like, who are you? So apparently there's a really big difference between men and women. So more men want to go than women. So, make of that what you will. And then old people just can't be bothered, really. They're just like, leave me alone. I don't want to go to the moon. You go if you want. Moon is something for the young. I guess. And then you got the top 10 reasons why people didn't want to go.
That's exactly what I wanted to see.
Yeah, exactly. Yeah. So I thought the main reason would be, I don't believe you that it's safe, but apparently that's only at 10% of the reason that of the people who said no. So they reject the premise that your safe return would be guaranteed, which comes in the question. Most people just not interested. There's nothing to do once you get there. So I don't know. There's no cinemas or whatever.
I love fear of flying. So kind of, I guess I see that, but like we're all flying through space. Well,
it's guaranteed safe. So you just, I don't really get it, but people not particularly interested apparently. And I imagine that would hold similarly, if not more, for Mars.
Too old is just brilliant as well, because that's basically that's the one I'm putting. To be brutally honest, I was just thinking, you not anymore. I've got too much on. I've got quite sore knees nowadays, actually, and that probably isn't a good.
I'll tell you. When I was at university, I remember people saying, 40-year-old people saying, "Oh, my knees." Oh, shut up, granddad. And now I wake up, or when I've been to the gym, and I'm just like, just feeling those knees now. Feel very, very sorry for what I used to say to those people. So so 2 rovers on Mars, lots of interesting physics going on Mars. We'll have to keep an eye on Ingenuity, see how long it lasts. But yeah, very interesting stuff going on. Lots of competition to be the first to discover if there's any life on Mars, and hopefully that competition will lead to some interesting results. I haven't seen any interesting science results actually, or too much come out yet. Maybe because I haven't been looking for them, but I'd have expected to see those more prominently if there'd have been any particularly interesting science or biology to come out. So
there's been a few interesting examples where you've got people on the internet that have found a particular picture of a rock and decided that it's clearly like a skull of an alien.
Oh, yeah, that was always going to happen, though.
Yeah, that's the most exciting things I've seen out of it so far, apart from the helicopter. Yeah.
So I'll have a look and see what the roundup is of the science that Perseverance done, and maybe we can look at that next time. Ramsey, anything else that you've noticed over the last sort of month before we close up?
I've just remembered one thing for you, actually.
Go on.
So
or any questions from anyone watching as well. If you want to ask any questions, feel free to shoot them out.
Well, while we're perusing the chat box, a few years ago we chatted about the UK GNSS program.
Yes.
And you
yes. What's the damn name? So for our viewers out there who might not be aware of this, so what are the 4 constellations of? We call them GPS, don't we? We do the partridge thing of calling the tannoy when it should be public address system, or Hoover when it should be vacuum. What are the 4 satellite constellations of GNSS, of which GPS is one?
Yes, the global navigation satellite systems we all enjoy are the American GPS, the European Galileo, the Russian GLONASS, and the Chinese Beidou systems.
And we use GPS sort of a shorthand, a sort of stolen.
Yeah, exactly. Yeah. The sellotape of the sat navs. And then when the UK had its interesting moment and Brexited, that meant we were going to lose access to all of the secure parts of Galileo, which is pretty important. And so we started looking into building our own global navigation satellite system. And this is still bubbling around. There's all sorts of things going on still about whether this program is going to happen or not, and all sorts of things. But you asked me years ago about the name of the program, and I said that it wasn't well known, but that there were some sort of suggested names. And
the Nigel Faragher Memorial Navigation System.
Exclusively for you, this is probably not available anywhere on the internet.
Excellent.
I have for you.
Can I guess?
Name that has been used.
Can you give me a clue first? See if I can guess it. Is it guessable?
It's an acronym.
It's an acronym.
Have you put any effort into this before today, or we'll be here a while?
Give me a clue. Come on.
The first word of the acronym is British.
Right. Of course it is. Brit.
You got any thoughts?
British. Oh, it's not BPS, is it?
No. Shall I just tell you?
Go on.
So the name being used internally, and I don't know if this is serious or a joke. I couldn't tell. It could easily be serious. The British Orbital Radio Navigation System, or the Boris.
No way. No way. Somebody's made that up. Surely. That you're pulling my chain.
So all I will tell you is that the person who told this to me off the cuff, unprompted from me, would definitely know if this was true. But because it's
they did think I was a Guardian journalist as well. You told me.
Yeah, but that's all on you. That's nothing to me. That's clearly what you portray. But
oh dear.
I obviously laughed, but it could be either way. Either my leg is being pulled, or it genuinely is the internal name.
So give us that again. The British Orbital.
I'll clarify that. I checked I would be okay to do this before I get myself thrown in a prison. British Orbital Radio Navigation System, or the Boris.
Okay, go with that. So we'd have GLONASS, Beidou, GPS, Galileo, and Boris, and it's going to be meme to hell.
Well, I still think my American friends said Brexat right at the start, and I still think that's absolutely perfect. That's exactly what it should be if we do build one.
I think we should go with that. Ramsey, very, very interesting, excellent roundup again. Anything that's coming down the pipe in the next sort of month that you think, or shall we see what comes about and then we'll round up some ideas for next month? Anything on the horizon?
Well, it's been very interesting how there's this constant evolution of like the Tesla stuff. I've seen a few more flying cars actually since we first spoke. Clearly, the flying car concept is also still really bubbling around. So we might see a few more of those. But I'm sure that the Tesla stuff is still evolving as to how they're going to decide what they're doing with all of their sensors. And I wouldn't be surprised if by the next time we speak, Ingenuity is in bits on Mars. So let's see if that prediction comes true.
You heard it here first. That's not going to make you a popular man, I don't think. But we'll see what happens. Ramsey, thank you so much for taking the time to discuss that with us again. And yeah, let's see what happens over the next month.
Cheers, Sam. Thanks.
Let me just see if there's any. No, we don't know questions, so we're good to go. And we'll pick up next month. So thank you guys for watching. Thank you again, Ramsey. And let's talk again soon, buddy.
Thank you, Sam. Bye for now.
Bye. Let me...